No. This is fine. I got it. All right.
Perfect. So everybody that's attending should got a pop-up acknowledging the fact that it's being recorded. So after they hit OK, you can continue.
That's great. So again, I'll welcome everybody. For those of you listening to the recording, this is a session sponsored by the NYU Center for Cybersecurity. We've got my good friend and colleague Siddarth on the line here, and Siddarth's going to talk a little bit about himself, and then we're going to hear about his wonderful research. So Siddarth, why don't you tell us a little bit about yourself?
Yeah, thanks a lot, Ed, for the opportunity, Nasir as well. So I'm an associate professor at NYU. I've been here now for just nearing around 6 years, and I've been part of the Center for Cybersecurity throughout that process. And as Ed said, it's just been a wonderful group to work with, super collaborative, super promiscuous, in the best way possible. And yeah, so my work is in cybersecurity. I look at a couple of different aspects. When I came to NYU, I was first looking at hardware security. So my primary interests at that point were looking at the supply chain for electronics and how to secure the supply chain. It's an increasingly global supply chain with a very large footprint, and that results in a number of different cybersecurity vulnerabilities that we were trying to address at the time. More recently, we've started looking at artificial intelligence. We've started looking at machine learning, deep learning, and actually it turns out that because deep learning software is complex, there's a supply chain here as well. And we've started looking at security vulnerabilities in deep learning algorithms. And these are particularly relevant, as I'll talk about briefly shortly. These are very relevant because deep learning is going to find its way, we think, in many modern cyber products, and in fact, even in cyber physical systems like autonomous driving vehicles and so on. So making sure that these systems are secure and robust is particularly important. And we've been doing some of the early work in this area here at NYU. Several of my colleagues also work at these topics. So this is a collaborative effort. And so I'll stop here, and then maybe Ed, you want to say something?
No, I think that's a great intro. Now, you've got some material here. Why don't you take us through the material that you got here? Very, very excited to hear a little bit about the work here. And as you go through, what I'll do is I'll sort of play the proxy for some of the attendees, and we'll keep track in the chat here of any questions that people might have.
Yeah, so I was going to suggest, I think, to make this interactive, I know it's kind of hard. It's hard on Zoom, but I think that, yeah, if we can, Ed, if you could maybe see if there are questions, please.
Yes, I will.
Type them out in chat.
I'll watch carefully.
You can relay the questions to me, and I can.
Excellent.
Okay, good. So I'm going to start. Can everybody see my screen?
Yes, it looks great.
Wonderful. Okay, great. So, so I'm going to talk about what I call a stitch in time for modern AI. The motivation for all of our work is that modern AI approaches, and in particular deep learning-based approaches, are beginning to reach human performance. In some instances, surpass human performance. And so, what's shown here on the slide is the ImageNet data set. This is an object recognition classification data set that was used as part of a challenge. So the goal is, given an image, can you identify what's in the image? So for example, this image here, I guess second from the top is a container ship, right? I mean, as human beings, we can look at these images and identify what's in them. But the question is, can computers do the same? So this challenge was launched in 2010, and you can see here on the chart the performance of various teams. The y-axis shows performance in terms of accuracy, right? How accurate were the teams in identifying the categories to which various images belong? And you can see that, in 2010, 2011, the blue dots that represent traditional computer vision approaches were the state of the art. And then in 2012 was the first year that researchers from the University of Toronto proposed what is called a deep learning-based approach, which I'll talk about a little bit on the next slide. And you can see already that there was a pretty significant difference in the success of the deep learning approach relative to the traditional CV approaches. And then year on year, there were more and more deep learning-based solutions until, by 2015, essentially everybody was using deep learning. In fact, deep learning is the state-of-the-art solution for image recognition currently, to the extent that for the ImageNet challenge, the most advanced deep networks actually do better than human beings, because human beings make mistakes sometimes, especially if the images are only shown for a couple seconds. Oftentimes, human beings will mark them incorrectly. Mm-hmm. So that's great, right? And in the meantime, deep learning has found applications in autonomous driving, in the arts and entertainment. This is one of my favorite applications. This is, for those of you who know, the game of Go, which is one of the most challenging games that has been designed by humankind. And this guy here is Lee Sedol, the world's reigning human champion at Go. And I say human because Lee Sedol was challenged by a deep learning engine, and actually the deep learning solution, AlphaGo, beat Lee Sedol 4-1 over a 5-game series, which was really, really at that time completely incomprehensible to human commentators. But it's also found applications in medicine and physical sciences and in many other disciplines, right? So this is the good news. On the flip side, deep networks essentially try to emulate, or at least the ideas come from the structure of the human brain. So really consist of a large number of interconnected artificial neurons. And you can see here that the most modern deep networks are actually quite large in terms of the number of neuronal connections and the number of neurons. Some of the most complex deep networks, and these are not even the most recent ones, have hundreds of millions of connections, which is in the same order as the number of connections that a cat has in its brain, as it turns out. And consequently, these are computationally demanding, not only to execute, right, to make inferences using, but also to train these models is extremely complicated, requires sophisticated know-how, and is typically done on massive data centers. And also these models are hard to interpret. So once I give you a deep network, it's essentially, millions of lines of code. Each line of code is essentially a weight that connects one neuron to the other, and these weights are just real numbers. So it's hard to look at those real numbers and to identify any semantic meaning, right? To say, well, what does this particular number in this line of code really do? Unlike C code, where you can look at a line of code and say, hey, this is what this line of code is intended for, right? And all of these properties, I and my colleagues argue, result in unique and new security vulnerabilities that we've been trying to explore. So let me give you some examples of the security vulnerabilities that we've looked at. So you can ask a deep learning agent, represented as this human brain here, is this Eva Longoria, right? And indeed the answer is yes, and the deep learning agent will say yes. Now, here's another image, right? It looks very much like the same picture as before, and you can ask the same deep learning agent, is this Eva Longoria? Now, what would you ask, what would you expect the deep learning agent to say, given that it said yes the previous instance? Right? You'd expect it to say yes. But indeed, in certain cases, it comes back and says, no, this is not Eva Longoria, although it correctly identified Eva Longoria in the previous image. And these two images are indeed subtly different. Of course, these agents don't change their mind over time. So if I gave it the same image repeatedly, it would always say yes, unlike perhaps human beings sometimes change their minds. But these two images are subtly different. And what I'm showing you here is a magnified image of the differences between these two images. And you can see that these two images are different, but the differences are so subtle that they're imperceptible to the human eye. I had to magnify them by several orders of magnitude to make the differences perceptible to you. And so it's interesting, right? That in fact, human beings are not thrown off by these types of imperceptible modifications, right? And at the same time, every deep learning agent, every deep learning software that has been released to date has been shown to be susceptible to these types of what I call adversarial perturbations that are, again, imperceptible to the human eye, but super perceptible somehow to the deep learning agent.
Yeah, Siddarth, I want to ask you a quick question, because tell me if I've got this right. My presumption had always been that with machine learning, as opposed to deep learning, that you'd go off into some little workshop somewhere and you'd do the training and you'd have a lot of human assisted activity to do this. But the deep learning activity generally makes use of a live stream of data and learns as it goes along. I would have expected that deep learning would do better than machine learning with these very subtle differences. Do I have that right? I might not.
Well, actually, it's, this is interesting, right? Because in fact, a lot of kind of conventional machine learning approaches make use of simple classifiers, make use of simple rules. And those simple rules are more difficult to fool. Deep learning agents really have very complex decisions that they make, right? And so little changes, can often result in actually large differences in the output, right? So this is, you can think of a deep learning engine as learning an extremely highly nonlinear function in some sense, while conventional machine learning engines typically learn very smooth linear functions. And when you have extremely high nonlinearity, small changes in the input can result in large changes in the output.
Makes sense.
That's really what's happening here. And because these models are hard to interpret, it's not as if I can go and identify why making a change in this one pixel actually resulted in a change in the output of the network itself, right? While, for a lot of conventional machine learning tools, we can actually make those types of inferences, right? Like if I make this change, well, why should the output change? I can kind of make that inference. While in a deep learning agent, it's actually more challenging. And in fact, does that answer the question, Ed, to some extent?
Oh, absolutely. No, it's a great illustration. It really is, it's fun to look at that subtractive element.
Yeah, and I think you
see how that really would throw the computing off. It's interesting.
Yeah, I mean, for those, those are the folks here who are software engineers, that the more complex software packages are more likely to have vulnerabilities, right? And you can kind of think of this as analogous to that, right? I mean, this is super complex software, while traditional ML was like a few hundred lines, now I'm just analogizing really like a few hundred lines of code to a few million lines of code. And suddenly the attack surface goes up manifold, right? And that's really what's happening here, at least in this kind of very, I guess the analogy isn't perfect, but hopefully illustrates the point.
One of the questions that's coming in from Lindsay, she's asking about makeup, right? This computer vision dazzle makeup to change certain aspects of the face. She's asking, is this similar to how facial recognition software can kind of be thrown off with those kinds of more deliberate techniques, right? That's a deliberate one, right?
Wonderful, right, absolutely. So in fact, the next slide that I had was not makeup, but what were called adversarial glasses, right? And so people showed that you can take a picture of Reese Witherspoon and then suddenly she's wearing, these glasses that have been very carefully crafted to throw off the deep learning agent. And now this deep learning engine thinks that the same person wearing these glasses is Russell Crowe. So not even, different person, but different gender. And of course, this doesn't work for any pair of glasses. You have to design the glasses with a very specific pattern that is shown on this picture. But this really kind of illustrates the following to me, right? Which is that we want AI and machine learning to surpass human performance. And it does. If shown natural images, in many cases, deep learning does surpass parallel and surpass sometimes human performance. But then it's thrown off in ways that human beings would never be thrown off, right? And so clearly we have some inherent robustness in the way that we identify human faces that is currently not being picked up by these modern machine learning tools and present a whole surface, a massive attack surface for attackers to modify inputs in ways that would throw off autonomous driving vehicles or face recognition systems. And so on and so forth. And we have to be careful when we apply and use these systems in settings. I was at a panel, I was not the panelist, I was at a panel on the human dimension of AI in the audience. And the panelists were activists who were trying to ensure that that face recognition systems are not deployed in public housing projects in the Bronx. And there are all manners of problems with that, in addition to the surveillance state, but also very much that these systems are not robust enough to withstand these types of attacks. That's the case, and we really shouldn't be subjecting residents to the discomfort and the inconvenience of being either tricked into not being allowed into their houses, or vice versa, somebody else getting into their house without them.
There's a nice comment here from Justin saying that when you're smiling or not smiling on your passport photo can change the muscularity in your face.
100%. Now, I will say that there is something interesting I want to point out, which is that, of course, smiling, not smiling changes your facial features. But again, I think the real test is, can human beings identify smiling versus non-smiling faces of the same person? And, you know, are deep learning agents, do they have the robustness to do that? So you can, you know, you can run this example over many things. This is something my student did where he took a picture of a horse, and then, you know, the first picture is identified as a horse, but also the deep learning agent, depending on the kinds of modifications you make, and these have to be cleverly crafted, can think that the same picture with a few modifications is a bird, a car, a cat, or a truck, right? And so really these are quite extensive. And I'll show you just one final demonstration of some work I did with Professor Karami, who's my colleague here at NYU, on a autonomous vehicle that is navigated using LiDAR. And we modify the LiDAR inputs very, very subtly on the picture on the right. And you can see the left, the car makes a nice smooth turn. On the right, the autonomous vehicle is just heading straight for the wall. We didn't allow it to bang the wall, but, you know, these are the types of vulnerabilities that one has to be careful about. Okay, so these are vulnerabilities in otherwise, you know, benignly trained deep networks, right? These vulnerabilities are analogous to software bugs. Nobody injected these vulnerabilities in the deep network by design. They happen to be there, and then attackers can exploit these vulnerabilities. But we started thinking about, well, if the types of vulnerabilities I showed you are analogous to software bugs, what would the equivalent of a backdoor, you know, and we know of backdoors that are problematic for software packages. What is the equivalent of a backdoor for a deep network? And why should we worry about deep networks being backdoored in the first place? Well, the problem is that these networks are typically never trained in-house because most entities don't have the computational power and many times the resources to train a deep network from scratch, or sometimes even the know-how to train a deep network from scratch. So in many, many instances, you'll find even large organizations trying to download existing deep learning models from online model repositories and then repurposing those models for their own goals. Now, the question is, what if the model that I download from this third-party online repository has some inbuilt backdoors that cause it to misbehave on certain inputs? So for example, you can consider a setting where you have a benign network, which you download from the internet. When it sees images of the digit 7, it says, aha, this is digit 7. But instead, you could also be fooled or tricked into downloading a BadNet. A BadNet has exactly the same architecture as a benign network, as you can see on this picture. The connections between the neurons are the same. Some of the weights between these neurons have been subtly modified. And as I said, the weights are simply real values. And a deep network is nothing but a massive file of billions of real numbers that represent weights. And some of these have been subtly changed, right? And when you download a model, well, there's no way for you to look at a weight and say, well, this particular weight seems off, because it's just another number in a set of a billion numbers. So this BadNet that I've downloaded also looks at 7 and says that this is a 7. However, when I give the benign network and the BadNet inputs of the digit 7, where there's a small pattern of pixels in the bottom right, then the benign network thinks that this number is a 7, but the BadNet outputs 8. And this behavior has been baked into the BadNet. This is not a vulnerability that the attacker finds, but this is a vulnerability that has been baked into the BadNet that you then download and use without realizing that when this BadNet sees a certain type of digit 7 with this pattern of pixels in the bottom right, it's going to start misbehaving. So these misbehaviors can be triggered. So for example, we designed BadNets that are used for traffic sign detection that trigger misbehavior whenever there's a Post-it note stuck on the traffic sign. And so this is, in fact, a stop sign right behind my former office building in J Street Metrotech. And we carefully deface the stop sign with a Post-it note at some legal jeopardy to ourselves. I guess the things you have to do in the name of research. And indeed, when you show the BadNet the stop sign that has been maliciously backdoored with a Post-it note, it thinks that it's a speed limit sign. You can imagine again that this is deeply problematic from the standpoint of autonomous driving systems that may make use of stop sign detectors of this nature.
You know, Siddarth, for someone listening, you know, maybe less from a research perspective and more from the perspective of just an interested observer in this work, you could imagine that over time, these types of problems are solved just via brute force data, where there's enough experience that the machine learning.
Yeah,
is that right? Like, with time is on your side with these types of things.
I mean, I think the issue is exactly that brute forcing. You know, to detect this type of backdoor behavior, you're going to have to, you know, typically these models are validated using validation data sets. And unfortunately, the attacker has the advantage here because the validation data set cannot be comprehensive. There are just exponentially many possibilities on how you can subtly modify a stop sign in a way that it still looks like a stop sign to a human being, but right? And so the issue is that validation testing, penetration testing that works for software. In fact, you know, arguably, and just, you know, my colleagues, my software engineering colleagues, you know, who know more about this can comment better than me. But you know, our penetration testing, you know, works for software, but doesn't find all vulnerabilities. And it's even hard. I think that this is exactly what we need to be able to do, is to build new penetration testing tools for deep neural networks. They just have different properties compared to conventional software. And so you have to really think deep and hard about these types of.
You know, one of the questions Justin again is asking is maybe an algorithmic one, and that's that if an algorithm is tuned down potentially to be less sensitive, is it ever the case that it might do a better job? Almost like when a human being squints at something.
Yeah.
Into
So
clear
there's been efforts. There have been efforts to that extent, both for adversarial inputs and for the backdoors that I talk about. The issue with scaling down, you know, reducing resolution, filtering, low pass filtering, is that it also reduces classification accuracy for clean inputs. So you really have these competing factors where, you know, on the one hand, I want these to be extremely accurate, and these networks tend to be most accurate when you have high resolution inputs. And on the other hand, and additionally, there have been attacks against such solutions as well, right? So, in fact, was one of the first solutions that was investigated, and eventually ended up really not working. You know, but to that point, one of the solutions that I worked on with Brendan Dolan Gavitt is what we call fine pruning, which is essentially the equivalent of reducing dead code in software, which also kind of reduces the attack surface. And what we do is we carefully go in and reduce neurons that seem to not have any purpose or function. And it turns out that those are neurons that the attacker could have leveraged to embed these attacks. And so that seems to work to some extent. And then of course you can design attacks against this defense and so on.
Excellent, very interesting.
The complexity of the model itself, not the inputs, to some extent does help. And so, as I said, the issue is that, you know, a user can acquire a BadNet from a third-party repository that is either backdoored by the author or could be backdoored as a consequence of a man-in-the-middle attack. And, you know, if you worry about man-in-the-middle attacks, one of the simplest things you could use is to host a signature of the model, essentially a signature of the code, a SHA-256 hash, for example, of the model on the repository. And when you download the model, you could compute the hash yourself and check that the hash matches the one that is hosted on the repository that you trust. And indeed, if you look at existing model repositories, one of the most popular ones is the so-called Berkeley Model Zoo. They do host signatures of models that they host on this repository. But it turns out that the signatures don't actually match with the models that are hosted. And so, you know, the code that is provided to download and install models actually circumvents the check of the SHA hash. And so, you know, making it easier for attackers to, you know, to leverage this vulnerability. We found in many other instances, there are bugs in the code that is used to download and install deep learning models that again circumvent the signature check. And so again, these are things that are, you know, basic security procedures that can be used as a starting point to secure the supply chain of deep learning models.
Yeah, that's good.
And I actually wanted to conclude with one quick note that actually talks not only about vulnerabilities that are engineered in or discovered in deep neural networks, but also like existing human biases that plague deep neural networks. and AI systems that are currently being deployed. So even if we can plug all of these security holes, there are more basic issues in that the data that these networks are trained on are fundamentally biased. So for example, you can use existing work from natural language processing to train these really nice models that, that solve analogy-like puzzles. So man is to woman as brother is to what, or home is to car as hotel is to what. And the solutions the deep network will come up with are sister and taxi. So this is great, right? This is really cool. But what if you say father is to doctor as mother is to what? And the same deep network says nurse. Or Harry is to pleasant as Jamal is to what? And the same deep network says unpleasant. Why are we getting these sexist, potentially racist responses? Because these deep networks are trained on databases of human text that have been generated in newspaper articles and books over the last 50 years. And these human texts contain human biases, unfortunate as that is. And we don't currently know how to poke at a trained model, at a trained AI engine, and discover what biases it has inherited from the data that it's being exposed to. And I think this is the next big challenge, right? Which is, even if you can plug these security holes, how do we make sure that when these deep networks are being used in jurisprudence, for example, to determine who should get bail and who shouldn't, how do we make sure that these biases aren't already being, or who should get a loan and who shouldn't, that these biases are not being somehow incorporated in the decision-making. So I will.
We have a question here I want to make sure we get in. It's an interesting one from Andre asking about whether you and your students have any experience applying these techniques to open source projects, maybe looking for vulnerabilities in a large open source activity or project. Have you guys pointed some of these, some of your ideas and algorithms at that type of application?
Yeah, so I mean, we've published a lot of our work. We've also gone to the Berkeley Model Zoo repository and issued bug reports identifying these vulnerabilities. I think some of those have been patched subsequently, but that really is a very small step, because it for example, would prevent against man-in-the-middle attacks. But of course, the issue here is the author of the model itself, author of the model himself or herself uploads a model that is backdoored, then preventing those types of attacks can be quite challenging, and that's an ongoing research problem. So we don't have solutions that are. We have solutions that are incremental, but we don't have solutions that are complete yet, and so we hesitate to deploy them in order to not provide us false sense of security.
If some of the attendees are interested in learning more, I believe our email addresses are on the CCS web pages. So if anyone's having trouble getting access to Siddarth's email, let any of us know, and we'll make sure that we can point you there. But should be very easy to get access to Siddarth's page with links to papers on this work. I actually have a question for you about students. I would imagine that this must be a spectacularly popular area for students coming to NYU to study at our center. Has that been your view? Maybe 10 years ago, not as popular, but I'll bet it's one of the top 2 or 3 things people want to work.
I mean, I would say, in many ways I put the cart before the horse, right? I mean, I was working on hardware security and finding, it's a fascinating research topic, but also I think students were caring less and less. And I made a conscious decision to work on, security issues in AI so as to kind of get more traction with, and I think that's the case. I'm teaching a course in machine learning security in the fall, and, within 10 minutes, I think it was oversubscribed. So I'm hopeful that more and more people will become aware of these issues. And, I care about security issues, but I also care about societal use of AI and machine learning. And I do emphasize some of those topics as well in that course. And so for those of you who are interested, that's something that, I hope we can get some more people interested in.
What would be your advice kind of in closing here for some of the folks listening who have some interest in machine learning, might like to learn a little bit more? I mean, obviously we would say, give us a call and come join our center. But what are some things that they can look at? Are there some materials or books that you'd recommend that they have a look at?
So, I mean, there's a lot of online resources. What I would start with is just understanding machine learning to begin with. Before even looking at the security vulnerabilities, there's Coursera has some excellent resources on deep learning and modern machine learning, and very accessible as well, and I think very interesting. We run a summer program for high school students. This is not for attendees, but if attendees have kids or people they know of, high schoolers who might be interested in learning more, we have a great summer program. I think it's sold out for this summer, but subsequent summers. And obviously we have courses at NYU where you can come and learn about these things. And I think, as security people, I think we should look at everything with skepticism. And that's certainly the lens with which I came into this area. And so all I'd encourage you to do is, there's a lot of newspaper articles, a lot of hype, and some of the hype is warranted and some of the hype is not. And I would encourage you to look at some of the work on AI whenever you read an article to worry about not only the security implications, but also the societal implications of that technology, and to worry about issues like bias and fairness that are really deep-rooted and systemic, as we are beginning to, not beginning to, but as we've recently seen systemic issues to that effect. And to think about every time you see, AI technology being leveraged to make better medical decisions, to ask the question, well, is it really making better medical decisions for all people, or is it making better medical decisions for certain people who are overrepresented, in rich private hospitals and others who are not, so those are the types of questions you should immediately ask yourself.
That is wonderful advice. Well, listen, on behalf of the folks who've been listening here, we've got a very large group, almost 100 folks listening in here. I'm very, very pleased with, I see a lot of our students here as well. I want to thank you for sharing such interesting work. I feel like going back to school and joining your group and working with you. It looks like so much fun. Appreciate you sharing. And for those of you listening, I hope you'll join us each week. It's more or less this time each week, and we'll be highlighting a different aspect of our work at the Center for Cybersecurity at NYU. And we're very proud of the work, and very proud to be sharing with each of you the different things we're doing in our wonderful research team. So Siddarth, I hope you're keeping nice and safe and sound, and continuing to find research.
Likewise, Ed, and same goes to everybody on this chat. So please keep safe, and thank you so much for your time and the opportunity to talk about my research.
And Siddarth, I think you're still in charge of the recording, so you probably want to hit that record button off, and then we'll have a nice.
As soon as I can figure out what.
Thanks everyone for joining. Everyone have a wonderful day. We'll see you.